Hello and welcome to this webinar, Battery Data Acquisition and Analysis using MATLAB. My name is Rob Gressley and I'm an application engineer at MathWorks. In a few minutes I'll be joined by my colleague Javier Gazzari, who will be going over the battery hardware and data acquisition process for our demonstration. First, let's take a look at what we'll be talking about today. First, I'll give a quick overview of how a typical data analysis workflow looks. In particular, we'll be looking at different ways to analyze data or pre-process our data before doing any subsequent higher level modeling. The demonstration that I'll be showing will talk about developing a custom data analysis workflow with MATLAB. Finally, I'll show and talk about a few different ways for sharing your data analysis work with other people, and then finally we'll wrap up with a summary and leave time for some questions and answers. To give an example of what I'm talking about and the types of things we'll be discussing in this webinar, I'd like to show one example of sharing a data analysis workflow, and that's doing it as a report. So if you take a look at this report, you can see by the title that we're pre-processing some battery data that we're going to be using in order to accurately model the battery a little bit later on. There's different sections in this report that describe the different steps that we followed while going through this data analysis process, from importing our data, smoothing it in order to remove some noise, fitting some different lines and curves to our data, and also filling in data that may be missing for whatever reason. And this report is documenting a process that was followed using MATLAB. And in fact, this report was published using MATLAB as the output of a MATLAB script. So one easy way to share your work with other people or to document it for use later is to place it in a report. And MATLAB makes it very easy to document your work and share it with other people. So in the demonstration that I'll be showing, I'll actually show how you can walk through starting from scratch and build up a MATLAB script to produce a report similar to this one that documents your data analysis process and allows you to share it with other people. So before I go any further, what exactly do we mean by data analysis? And for this particular webinar, we're talking specifically about, acquiring data from a battery and then removing noise, removing outliers, pre-processing it before we can do some modeling of the battery. But in general, what do we mean by data analysis? And it really encompasses a wide range of areas, as you can see by the different types of tools that are used in data analysis. Everything from a simple spreadsheet to more specialized applications, general purpose programming languages can be used many times to do data analysis as well. And then we also have technical computing languages like MATLAB. So what exactly is MATLAB? It's a high-level programming language that's also coupled with an interactive development environment. So MATLAB is very commonly used in different areas of science and engineering. For anything from data analysis and visualization, developing algorithms, and it's also a full-fledged application development environment. In the automotive industry, you see MATLAB used very commonly in all different types of data analysis. And it's also being used heavily to model and simulate different systems on a vehicle. Regardless of what specific data analysis task you're following, chances are your workflow can be mapped into one of three basic steps. First, getting access to data from some data source. And commonly, data comes to us in files, it comes to us from different software applications, or in our case today, we're actually collecting the data from a piece of hardware, a battery that we have some data acquisition equipment connected to it. Once we get the data from any of these sources, ideally we'd like to bring it all into a single environment where we can do our data analysis work, algorithm development, and so on. And MATLAB is really well suited for these different types of tasks, and MATLAB is really well known in these areas as well. But then once we have done our analysis work, we'd like to take that and share it somehow, either deploying it, generating some embedded code that runs in a processor, or something as simple as documenting our work in a report. And a key takeaway of this webinar is going to be how can we automate this process, moving from the different phases of this workflow, allowing us to really develop the workflow once, automate it, and then apply it to any new types of data that we collect. So that will be the key emphasis of this webinar, which is the ability to go through the different phases of this workflow using MATLAB and also automate the process as well. So before I go into defining our problem statement and going into the demonstration, at this time I'm going to pass it over to my colleague Javier, who's going to give an overview of the battery hardware that we use to collect data, and he'll also show you an example of how we actually acquire the data and brought it into MATLAB.
Here's a brief description of the hardware to be used to acquire the experimental data that we will analyze later using MATLAB. Here is the battery that energizes this electric motor that moves the drill. We will acquire voltage and current from that battery using these data acquisition cards that are connected to the battery and via USB directly to my laptop computer. In this way, I can stream experimental data directly into MATLAB for analysis. In addition to that, I have a real-time computer that contains the model of an electric vehicle. That model is going to allow me to know what level of current I need in order to move the vehicle following a certain driving cycle. And that is going to determine with how much current I am going to be discharging the battery at each point in time. Finally, using a vehicle network toolbox, I can communicate with the car model using CAN protocol. Here's a brief example of data acquisition. I have a script here that measures the voltage and current as I explained before. This window is going to show the voltage around 22 volts total for this battery at the top, and the bottom graph is the level of current, which is pretty much zero because there's no nothing energized at this point. So the battery is at open circuit. Now, for a brief example, let's see what happens if I momentarily disconnect the battery. I should see that the voltage drops down to zero, as you can see in the plot on the screen. And then when I reconnect it, the voltage should quickly go back up. This is something that we will use later to show smoothing for noise reduction and also interpolation in case I have some data acquisition dropouts. Then I can go ahead and stop it. I have my data in MATLAB in here. And the graph.
Now that we've seen the battery in action, let's take a look at how we can develop a custom data analysis workflow in MATLAB to process that battery data. Just to formalize our goal and our approach, we've captured the battery test data, and what we'd like to do is really clean it up to allow us to more accurately estimate some battery parameters and model the battery at a system level. So the overall approach that we'll take is to import the data into MATLAB, visualize it, and then implement and automate a workflow that processes the battery data to do different things like remove noise, replace outliers, subset some part of the data that we're interested in. So we'd like to automate that workflow and then share it in different formats, as a report that you saw before, as well as an application for analyzing this particular type of data. Whenever you're working with real-world data, test data, data that comes with hardware, there's a number of challenges that you may run into. With the data itself, you may have some issues with just accessing the data, managing it, and also coming up with unique ways to visualize the data. The data quality also might be suspect. You may be trying to combine data that has different sampling rates or that were sampled at different times. There may be data that's missing, and you may need to have ways to handle that. Some of the data may be bad, and you may need to identify which ones those are and have ways with dealing with that. So all of those challenges fall under the umbrella of really analyzing the data and pre-processing it and preparing it for any subsequent higher level analysis that you would like to do. So at this time, let's jump into MATLAB and get started by importing the battery data and seeing the different ways that we can start analyzing it. This is the MATLAB Desktop. On the top of the screen, we have the tool strip, which gives me access to commonly used functionality. The command window allows me to interact with MATLAB. The workspace holds any data that I bring in from files or devices and allows me to view it. And the current folder browser lets me look at the files I have on my computer. I'll talk in a little bit more detail about the different components of the desktop as we work through the demonstration. The current and voltage data captured from the motor and the battery are contained in these ASCII files, one for current and the other for voltage. I'd like to bring that data into MATLAB. To do that, I'm going to use this import tool, which will allow me to visualize the data that I'm bringing in and decide how it should actually be brought into MATLAB. The text files contain two columns, where the first column represents the time points where data was captured, measured in seconds. So this is quite a long data acquisition here. While the second column represents the actual data. In this case, we're bringing in current data. So I can choose what variable name I would like MATLAB to use for both the time points as well as the actual data values. Using this tool, I can choose what part of the file I'd like to bring in, how I bring the data in, as well as how unimportable cells are handled. So for instance, if there's data missing, I can choose within this import tool how I'd like for that to be represented in MATLAB. Click on this button to import the data into the MATLAB workspace, which I can verify by going over here and seeing that these new variables for time and data were added into the MATLAB workspace. The other thing that this import tool allows me to do is generate either a MATLAB script or a MATLAB function to reproduce this import process. With a function, this will automatically generate some MATLAB code that's parameterized. It contains all the code necessary to bring in files of this data type, and to reuse this code on multiple files, all I need to do is change the file name when I call this particular function. So let's see an example of that. I've already pre-saved a MATLAB function that was generated by the import tool called import voltage data, and here I'm specifying the voltage that I would like to bring in the voltage data file. So I can execute this function, and as you can see, it brings the voltage data into MATLAB. I can also do the same thing again with the current. It turns out that the current and the voltage data file formats have slightly different formats, so I can create functions for each type of file that I'd like to bring into MATLAB. Now that the data has been brought into MATLAB, I can visualize it by using a plot. You'll notice that along with the plot appearing, MATLAB also puts a command here in the command window that will be useful later on if I want to recall this plot for later or make it part of a larger automated process. Right, so we have a plot here of current versus time. You can see that this signal is very noisy, so what we'd like to do is really smooth out this data, and we have some time where the motor is not running, the battery is not being drained, so current is 0. Then we have a relatively constant current for a certain length of time, and then finally the motor turns off and the current goes back to 0. If you'll note, the values here on the y-axis are quite low if they were measured in amps. And the reason for that is that the way we're measuring current is actually by using voltage across a shunt resistor. So the values here are actually in volts. To get amps out of that, we need to multiply our current values by a scalar value representing the resistor. So that's going to essentially convert the volt values that we captured to the corresponding amps that were flowing through the resistor. Also, with the voltage data, we're using a voltage divider in order to reduce the voltage to a level that's safe to be handled by our data acquisition device. So to get from the recorded voltage values to the actual voltage values, we need to multiply that by a factor as well, in this case a factor of 2. Alright, so now if we look again at this current plot, we see that it's the same, except the y-axis is on a different scale. So here between 1 and 1.5 amps worth of current were coming out of this battery. And then if we look at voltage, you see that the battery starts out with a voltage around 20 volts, and then it tapers off down to around 16 volts. I'll get back to the voltage here in a second, because we see that the voltage signal is also noisy, which we'll deal with that in a second. But first, let's go back to our current waveform. Again, we see that this is pretty noisy, so we'd like to have a way to smooth out this waveform before we continue with our subsequent analysis. There's a variety of different ways that we could do that in MATLAB, and a very common question in general is, what types of functions does MATLAB have to do a particular task? Or how do I know which function to use, or how do I use a particular function? I can use the documentation to find out the answers to these questions. One quick way to get access to the documentation is through this function browser button next to the command window, and that's going to open up an index of all of the MATLAB functions I have installed, and I can search for them or I can browse. So one thing I may want to do is smooth out some data. I can see different categories or different functions that pop up in the search results. Under smoothing, we see some options provided by the curve fitting toolbox. One way you could smooth data is actually to fit a curve or a surface to it. So you see those options available. We also see a generic function here called smooth that smooths the data that we have in our vector using a moving average filter. A moving average filter is a very simple way to smooth data by taking averages of samples in a particular span. And if you have a signal that's been corrupted by random noise, the effect of the averaging actually starts to remove some of that noise because they end up canceling each other out if they're positive, negative relative to the actual signal level. So in the end, you end up with a smoother signal. Using this function browser, I get an overview of the function, and then from there I can quickly access the documentation page for that function. And typically what I'll do if I'm learning how to use a function for the first time in MATLAB is I'll go to its documentation page, and within that documentation page I'm going to find different examples of how to use the function. The examples create some realistic data and show how you can apply the function to the data. So typically what I'll do is just take some example code and start modifying it to meet my needs for whatever problem I'm trying to solve. So let's do that with our current data. I can use the smooth function. Reminds me of the inputs that are needed. In this case, I want to smooth my current data. And then I'm going to assign the output of that to a new variable called smooth current. Now if I create a plot, we'll see that the current signal is still noisy, but it is less noisy than the original result that we had. One thing we can do now is start looking at the different parameters that are available for the smoothing function. One of the parameters that's available is the span, so the number of samples that you're averaging to create each successive point. There's a default value that is used, but I can also modify it. And in general, increasing the span will serve to remove a lot more noise, but at the same time you'll also start losing the shape of your original waveform if you increase the span too large. So I can quickly use the command window, use the commands that were saved, interact and experiment with different spans. So let's say in this particular case this looks like a much cleaner waveform. A lot of the noise has been removed, but we still have some of the original shape of it, and this result will work for the rest of my analysis. So we'll leave it at that. Now let's go ahead and compare my original data to the smoothed waveform. I can quickly do that by selecting all the variables and then creating a plot of multiple time series versus the first input. So here we have our blue signal, the original signal. Turn on the legend. And then the green line, which is only faintly visible, is the smooth current. I'd like to fix that line. So I can use this plot tools capability to quickly go in and decide exactly how this figure should look. So for my current, I'm going to change the color of that line and also make it a lot thicker so it's more visible. With the axes, add some grid lines and also add some labels. On the axes, so that's current in amps. And now the title here is going to be the effect of smoothing on my data. So I can quickly use this tool to make the figure look like how I want it to look. And then, similar to with the importing tool, now that I've done this interactively, I can generate code to reproduce this later on. So this generating code takes this figure that I've created and automatically generates a MATLAB function that will reproduce that figure. And if you've done programming in MATLAB, worked with graphics, you'll see a lot of familiar commands in this code. You can modify this code to make it more relevant to you, or you can just start using this code as a way to learn about how to work with graphics in MATLAB. So now if I save this, the nice thing about this is that the generated code is a function, so I can pass in new data to this function that I've captured and reuse it on additional data sets, which I'm not doing here, but I would just have to change the inputs and the actual data within those inputs in order to accomplish that. Alright, so we've smoothed out the current. Let's take a look at the voltage. So again, we'll take a look at the voltage data. Whoops. There we go. And we could actually use a moving average filter on this data as well, but it also looks like this data follows some sort of an equation or some sort of a trend that we may want to use as a means of fitting to that data. Also note that at the beginning of our waveform and then at the end of our waveform, we have periods when the motor is not running, and we may not want to actually include these beginning and ending points in our fit. So we can do that by removing both the data here at the end, the beginning of the waveform, as well as the data at the end of the waveform. One very simple thing that we can do now is actually use our smoothed current here as a ways to quickly index into our voltage data and only pull out the voltage data that we're interested in. So here we're saying that we're only interested in the voltage data when our smooth current is greater than 1. And if you recall from my original plot with the smooth current, when the battery was being drained, when current was flowing out of it, the current went above 1, and then when the battery turned off, it dropped below 1. So this is only pulling out the points where the motor was running and the battery was being drained. Now I can do the same thing with the time and create an updated plot. And now we only have the part of the curve where the battery is draining and the voltage is actually decreasing. So let's see how we can actually fit different types of curves to this data. For that, I'm going to use a curve fitting app that's part of the curve fitting toolbox. Many different apps have, or many different toolboxes actually, have apps that allow you to perform common tasks interactively. You can also get different apps online from MATLAB Central, and you can create apps to give to other people. So with this curve fitting app, it's going to allow me to choose which data I want to fit. So in this case, my voltage data. And then choose what type of fit that I would like to use. So by default, it's going to try and choose a very basic fit to the data. So in this case, a 1-degree polynomial. But I can experiment here with different degrees of a polynomial fit, or I can choose from different types of fits that are provided by the toolbox that are fairly standard. I can also specify my own equation. If I have an equation from a paper or a textbook, or that I've derived that I think should match up pretty well with the data that I have, I can use this custom equation box to specify that equation. I can also choose another type of fit called a smoothing spline, which is similar to a moving average filter, except it's a little bit more complex. So it's a piecewise polynomial that serves to smooth the data. I can experiment here with different types of smoothing parameters. right? So here I can choose different smoothing parameters. I can interactively tweak that parameter and start seeing the effect that that has on my fit, both visually, and then also I can start looking over here at these goodness of fit statistics, R-squared value, root mean squared error, and so on, which give you a quantitative idea of how good your fit is actually doing. So you can try out multiple fits here, compare them within a table, and then you can also generate code from this fitting process using the curve fitting tool. Okay, so that value looks pretty good, so let's generate code from it. And again, this code generation process creates a function where you can pass in new data and it'll reproduce that fitting process. So now I'm going to save this function and use it to create a fit. We can see visually the original data as well as the line that's being fit to it. And now for smooth voltage, I use my model, pass in my time vector, and that's going to give me the smoothed voltage curve, which I'm now plotting on top of the original voltage data. Alright, so now we've brought our data into MATLAB, visualized it a little bit, and we've also smoothed the data and extracted out only a part of the data that we're interested in. So these are all tasks that you would commonly think of for pre-processing data before going on to more advanced analysis or model development. And so far I've been automating individual steps of my workflow as I've been going through. You see there's a lot of commands here that are in the command window as well as within the command history. So the command history has been keeping track of a lot of the commands that I've been writing and MATLAB has been putting there as well. And now I can use this command history to automate the entire process. So let me just select the commands here that I would like to use. Subset out the voltage data, create a model, smooth, and then create this plot here. Alright, so I've selected a larger process I'd like to automate, and I can do that by creating a MATLAB script, which takes the commands and puts them into the MATLAB editor. And now I can run this script, and it's essentially going to repeat this entire process very, very quickly. So I've automated the individual steps, quickly combined those steps into an automated script, and now I have something that's reproducible. If I get new data, or if I have new files I want to use, I can just change them up here in these first two lines for importing data from new files. So the last thing I'd like to do with this script, I've automated it, but if I wanted to capture the results of this script in a published format, I can use MATLAB's publishing and reporting capabilities. So on this Publish tab, I can see the different types of markup that I can insert into my report. And now I'm going to just quickly add in a few of these sections here. Sections are useful not only because they turn into sections in your published report, but also because you can use it for kind of like flow control in your script. So here I can highlight a particular section, hit run section, and it only executes those lines. So it's useful if you're working with a larger script, if you just want to focus on one part of it at a time. So I'll give this section a title. So this is going to import data and scale it. Right here, I'm going to say smooth the current and isolate voltage signal. Here I'm going to say smooth the voltage using a smoothing spline. But you can type in whatever section titles and whatever comments that you'd like, add in any additional markup that you'd like, and then when you publish your MATLAB script, it's going to run the script, capture all the outputs, and it's also going to capture whatever sections and comments that you put in and integrate those as part of the final report. So we see that I have 3 different sections for the different sections of my report, and then also the descriptive text I type in turn into comments. And it captured all of the additional visualizations and the outputs that were produced by my MATLAB script. So I've shown you a way to interactively work in MATLAB, automate the individual steps, automate the entire process, and then generate a report automatically. What I'm going to do now is open up a report that was already created. And if we scroll down and take a look at the different parts of this report, we'll see a lot of it should look pretty familiar, some slightly different visualizations, parts of it. The section that I'd like to jump to is called What If We Have Missing Data? Because so far the data that we've had has been continuous. There haven't really been any missing data samples, but that is a common problem we may have to deal with. So that's what I'm going to be showing in the remainder of the demonstration. So what are some techniques to handle missing data? One of the simplest things you can do is if you have an element in your data set that's missing some data, you can just delete it. I mean, the advantage of that is that your estimates will still be unbiased, assuming that your data is missing at random. The downside of it is it reduces your sample size, which could cause some issue if you have a relatively low sample size to begin with. It's also relatively easy to implement because MATLAB functions will automatically handle listwise deletion in many cases, and you can also easily do manual filtering using the logical indexing process like I showed earlier. You also may want to substitute or replace the data points that are missing with some reasonable approximation. And that can be very important when the rest of the data that's part of the elements that have missing data, the rest of the data that's there is too important to exclude. So you want to be able to keep that good data while replacing the missing data with some reasonable approximation. So the challenge then becomes what really represents a reasonable approximation. In any case, your error estimates will be biased as a result of doing this substitution process. So if this particular data point turns out to be missing, we could replace that with the mean of the surrounding data points, the median of the surrounding data points, perform a linear interpolation between the surrounding points, the 2 surrounding points, do some type of linear regression, or some more complicated model like a nonlinear regression or a smoothing spline. So you can see that there's quite a bit of variance between all these different means of substitution. So the ability to try out all these different means, see what the results are, and decide which one is most appropriate and be able to do that quickly and interactively is really what MATLAB brings to the table for these types of substitution problems. So to take a look at that, I'll go back and look at our report of the published script where we're going to set up kind of a hypothetical scenario, like where you saw Javier disconnect the battery from the rest of the system and the voltage and the current dropped to 0. So we're going to simulate that for a few seconds here. So you can see we have our original data, and then for a time for the voltage and the current, the sensors drop off and report 0. So first let's take a look at really a deletion. So here we're replacing those zeros with not a numbers, which means that we're going to be able to continue to use this data with the rest of our MATLAB functions, but the zeros that are there aren't going to bias the results at all. It'll just act as if these data points weren't even there. So things like statistical calculations or fitting curves will just basically ignore those missing data points. Whereas when they were 0, those zeros would have affected the outputs of the calculations. But this may not be enough. We may want to actually fill in some data points here, some reasonable approximations. MATLAB comes with a variety of functions that make it very easy to do this. For instance, for a simple interpolation, we can perform either a linear interpolation or a cubic interpolation between the different data points. And you can see that for each one of these, we do get slightly different results. But we can quickly try these by calling the interp1 function in slightly different ways to get a result comparing the linear interpolation and the cubic interpolation, and we can also see how they compare with the original data that we had. There's also a spline interpolation. In addition to the nonlinear regression, mean substitution, median substitution that I talked about in the slides, this is just one example showing a more sophisticated way of filling in some missing data, and that is a spline interpolation. So that's a piecewise polynomial. It has a certain order, and then it can be used to predict the missing values. So it takes into account the rest of our data set, and then we can use the resulting polynomial as a ways to get a prediction. So you can see that for this relatively dynamic current data, in this particular case, a spline interpolation does a pretty good job. That may not be the case for all data sets, but again, we can quickly use the built-in MATLAB functions. In this case, we use the smoothing spline function out of the curve fitting toolbox in order to quickly get a look at the result here of a smoothing spline and compare it to our original data. And again, we have all this documented in a report that was published automatically with MATLAB. Let's recap our workflow. First, we acquired some data from some files that we had saved. We also could have directly acquired the data from the data acquisition hardware, as Javier did during his example. We brought the data into MATLAB, where we did some data analysis and modeling, and then finally we took our results and shared them as a report. The tools that we used were MATLAB, the statistics toolbox, and the curve fitting toolbox, and Javier used the data acquisition toolbox to acquire the data directly from the hardware and bring it into MATLAB. Now let's take a look at some of the different ways we can share the work besides the report that we just saw a few moments ago. If you'd like to share applications with other people who have MATLAB, we have MATLAB apps that allow you to package up an application consisting of a user interface and some functionality you develop and quickly share it with other people who already have MATLAB. You can also take your work and share it with others who do not have MATLAB using standalone executables, deployable components, and web components. I'll talk in detail about that in just a second. If you'd like to really distribute across a large scale to many different users, perhaps across an entire organization, we also have a production server that will allow you to do that. So first, MATLAB apps are interactive applications that allow you to perform different tasks. We saw examples of apps for curve fitting in particular during the demonstration. There are some other apps as well that come as part of MATLAB toolboxes, and you can also build your own apps and share them with other people. It's a very simple process to build an app which creates a single installation file you send to an end user, and that user double clicks on the file to install it in their MATLAB, and they get access to it from there. So it's a very easy way to take what you develop in MATLAB and share it with others who have MATLAB themselves. For deploying applications with MATLAB to people who do not have MATLAB, you can use a tool called the MATLAB compiler, which generates standalone executables or shared libraries that can run without a MATLAB license. There are also tools that sit on top of the compiler called builder tools that will target specific applications, such as an Excel add-in, a Java package, or a web component, etc. So this slide gives you an overview of the products and how they relate to each other. How they work from a technical perspective is that you use MATLAB and any toolboxes you have installed to develop an application. You can then run that application through the MATLAB compiler to generate a standalone end product, in this case a Windows executable file. You can then take that file and send it to your end user, and they can run it without having a MATLAB license installed. They need to install something called the MATLAB compiler runtime, which contains the necessary libraries that allow them to run the MATLAB application that you send them, as well as any additional MATLAB applications. So the MCR is a one-time install, and with the MATLAB compiler, it gives you the license to distribute the MCR to as many people as you like, and also develop or distribute the compiled applications and shared libraries to your end users as many times as you like as well. This approach works very well for distributing MATLAB applications, MATLAB functions that you write to a large number of people. If you'd like to deploy MATLAB functionality across an entire organization, we have a tool known as the MATLAB Production Server, which allows you to create a central location for managing MATLAB analytics and analysis tools that you develop that is able to serve a large number of concurrent requests. This would be a very difficult thing for an end user to develop. It would take a lot of time. So the MATLAB Production Server provides an off-the-shelf solution for that that's really very appealing to application developers. For more details about this, you can look on our website for more information on the MATLAB Production Server. At this time, that wraps up today's presentation. We saw how MATLAB fits into a data analysis workflow. We saw an example of using MATLAB to develop a custom process for pre-processing battery test data. And then we also briefly talked about different ways to share that workflow with other people. Thank you for listening.